Water is flowing through a pipe entering at 20 degrees Celsius and 0.20 megapascals. We can envision this using a little picture. So this little circular pipe ends up like this. It starts at 2.50 centimeter diameter and exits through 0.60 centimeter diameter with a final velocity of 6 meters per second. So we can visualize this, putting it in here. Vel2 being 6.0 meters per second. This diameter here, D2, being 0.60 centimeters. We know that the initial diameter here is D1, is 2.50 centimeters. And we also know that the initial temperature is 20 degrees Celsius, and the initial pressure here is going to be 0.20 megapascals. And that's about all we're given. We are being asked to find the velocity at the outlet in meters per second, as well as the mass flow rate through this apparatus. Remember, as we are going through any of these types of scenarios, unless there is some sort of chemical reaction or some sort of stated accumulation, the mass flow rate has got to be the same going in and leaving. There is no accumulation, there is no consumption. So as we're going through this, we're going to find these two variables. The two systematically deal with thermodynamics problems, we always start with three-pronged approach. The first one is to state the assumptions and the givens. So what are we given, and what are we going to assume? We know it's water. So since this is water, we cannot use the ideal gas law. We could potentially use some sort of a liquid equation of state. That's not usually used because it's not very elegant and takes quite a bit of computing power. So what we're going to use is steam tables, or the tables at the end of a thermodynamics book, or some sort of a reference book. So the equation of state that we're going to use will be tabular, right? And when not given, we do an interpolation of sorts. Then we need to state whether this system is open or closed. Well, since mass is not confined, mass flows in and mass leaves, this is going to be an open system. Control volume analysis. Since this is a liquid water, we're going to assume it's going to be incompressible. There are no other assumptions. We don't know if it's isothermal, we don't know if it's isobaric, we're not given any of those types of assumptions, so we won't use any of this. In addition, we can also state here that we're using the SI system. We're not going to deal with imperial system. Okay, after we do the assumptions and givens, then what we do is we try to fill out the state. We do some sort of a table with states. We only have two states, the entering state and the exiting state. So we're going to just deal with these two. Again, here, when we're dealing with these entries, we can put any state variable we wish that is going to be helpful to us. Potentially one could put many. There's no need to always. Just put whatever is pertinent, whatever is given to you. You know there's a pressure, you know there's a temperature, you know there's going to be some sort of a volume attached to it as well. We also know we're given information about the velocity, and we're be giving information about the diameter, and we're being asked to find the mass flow rate. Not being given anything else or being asked for anything else, just won't state anything else here. We know that the initial pressure is 0.20 megapascals. The initial temperature is 20 degrees Celsius. We don't know the initial volume, specific volume that is. We don't know what that is, but we can look it up on the table. Now, if you go back to your the back of the table of a thermodynamics textbook, or some sort of a reference table, a steam table of sorts, you only need two state variables to be able to figure out the third one. Since this is a one state system. In this case, then, the volume ends up being, if you look it up, is 0.001002 meters cubed per kilogram. Note here that I am still sticking with SI here. Now, since this is incompressible, I can also state that in state 2 is going to have the same specific volume. I am not being given any information about the temperature and pressure. Likely the temperature is not changing, but I don't know. I don't know what's happening with the pressure. It is likely changing since there is a change in diameter. But I don't know, so I'm going to leave this blank. And to be honest, in this particular question, we won't even need these two. Now, the initial velocity we are given is going to be 2.50 centimeters. My initial diameter is 2.50 centimeters. The exiting diameter is going to be 0.60 centimeters. We don't know the initial velocity. This is what we're being asked for. We are given that the exiting velocity is 6.0 meters per second. We also don't know the mass flow rate, but remember, it's the same for both. So I don't have to solve for state 1 m dot and state 2 m dot, just the one. Okay, so this is how we do this usually. Step 1 to state the assumptions, step 2 to do the states and to fill out whatever we can. We cannot really fill these two. Ordinarily one would, but we can't in this particular case. We're not given enough information and we won't even need them. And now, once we're done with the states and all that we can fill in, we then go on to dealing with the actual laws. So in our case, this is a first law analysis. We're going to be dealing with first law, open systems. Now, when you're dealing with first law open systems, you typically need two equations. You will need a continuity equation and you will also need the first law open system. Now, in our case, in this particular case, we won't even need this. We just are going to deal with the continuity equation. Dealing with the continuity equation, well, what do we know about that? We know the continuity equation says that the mass flow rate must be conserved. That's what the continuity equation says. M dot is constant throughout. M dot is going to be equal to the initial area, the initial volume, velocity, divided by the specific volume, like that. And it's going to have to be equal to the exiting area, exiting velocity, divided by the exiting volume. Okay, specific volume, that is. All right, what are we given here? Okay, so what I'm going to do is I'm going to, using this, try to find the velocity right here, the initial velocity. I'm going to go for vel1 dot. What do we know? We know it's incompressible, which means that these two go away. We also see that here at the table. They're equal. So in this particular case, we know that A1 vel1 is equal to A2 vel2. Cool. Now, what is A for a circle? What's pi r squared? I don't have r, I have d. No big deal, so I'll call d over 2. So pi times d over 2 squared times the initial velocity equals pi times d over 2 squared times the final velocity. Cool. So I have pi d1 over 2 squared velocity 1 is equal to pi diameter 2 over 2 squared velocity 2. Pi's go away. Quite frankly, the 2's go away, or the 4's. They go away. So I really get d1 squared vel1 is equal to d2 squared vel2. Okay, do I have them? I have them all. And I wrote them here at the table, just for easy reference. I know the initial diameter, I know the exiting diameter, and I know the exiting velocity. So I'll just plug them in. Note now that I don't have to convert this to SI units because dimensionally, these two have the same unit and these two have the same unit. Technically, one could put this in inches as long as you're consistent, and this in meters per second, and still be able to get meters per second out. Okay, because we're just dealing with conversion factors. So I will put that, won't even convert to meters for this particular case. So I will put 2.50 centimeters squared times vel1 is equal to 0.60 centimeters squared times 6.0 meters per second. Then it's just easy to solve for velocity 1. Just divide through by 2.5 squared, and I get that the initial velocity is going to be 0.346 meters per second. And that solves part A. So we know here, this guy here is 0.346 meters per second. Now we're being asked for the mass flow rate. Note that I won't even need to use the first law for this because I know that the mass flow rate at any one moment is equal to A1 vel1 over volume 1. And if you look now, we just solved for vel1 right here. We know the initial volume and we know the initial area, so we can just put them all in here and get the mass flow rate. So let's put that over here. Mass flow rate is going to be, and I can use either the entering area or the exiting area, whatever. I have A1 vel1 over the specific volume 1. And remember, I have all of them. So m dot is going to be, well, in this case, I do need to convert my diameter to meters to make this all consistent. Otherwise, I'll have a mishmash of different units. So I will need to convert my diameter, which is currently 2.5 centimeters, to meters. So what I'll do is I could either convert that outside or I could convert that inside. Doesn't really matter. Remember that the area is pi r squared. So pi, and I need r squared, but I have diameter, so it's 2.5 over 2, but I need to convert that to meters. So 2.50 centimeters. Remember, I need to divide that by 2 to get the radius. Now I have this in centimeters. I will convert this to meters. So now this thing is pi r squared, and this r here is going to be in meters. So this thing is in meters squared. So I have pi r squared, that's the area, times the initial velocity, which is given to, we just solved for, 0.346 meters per second. And then you divide that by the volume, the specific volume, which we just got from the table to be 0.001002 meters cubed per kilogram. Remember now, I selected A1 vel1 vol1. I could have potentially used A2 vel2 vol2. It would have given me the same thing. I would have changed this 2.5 to 0.6. I would have changed this 0.346 to 6, and I would have kept this thing the same. Either way, the m dot would end up being the same, the m dot being 0.1693 kilograms per second.